Okay. Right. So this is the beta decay of a tritium atom, right? And we're looking for energy released, right? And energy is the conversion. We have loss of mass here compared to the initial amount of mass in our tritium atom. And that loss of mass becomes the energy. So our energy would be, right, the mass of our tritium minus the mass of our helium atom plus the electron. All right. So this, I don't know if that's going to be equal to, right? That's going to be equal to our energy. Good. That's what we got conceptually. So now we just have to look up those masses. So I turn to Appendix B in the book, which is on page A12. You don't have this memorized? What have you been doing this weekend? Yes, you will be given it all the information you need to give. Yes. So here we go. So the atomic mass of tritium is well, am I looking at the right one? 3.016049. The atomic mass of helium-3 is 3.01604. No, I'm confused. 0.029. Now, honestly, I'm not sure why, because when I did this, the mass of an electron is, where's my notes? It's a little easier if I just look on my notes instead of looking up in the book. The mass of the electron is 0. Where is it? Hold on. I have it written down here somewhere in my notes. I can't find it. Here it is. 0.000549. Right? And if we put that in here, the total mass is greater than the initial. So we're ignoring the mass of the electron. And yet, but there's another problem, like the third problem I had you do. To get the answer in the book, you have to use the mass of the electron. And I'm not sure why we choose to not, we're ignoring the mass of the electron here, but in this other problem, when we do number 27, the book wants you to use the mass of the electron to get the book's answer. And honestly, I'm not sure why. And when we can choose to, why we choose to ignore the mass of the electron here and not in the other problem. I don't know. Maybe. In number 9 here that we're working on, it says, oh, that's why. Nope, I'm reading the wrong problem. Hold on. We're not doing number 9, we're doing number 18. How much energy is released when tritium decays by beta emission? And in number 27, it says a nuclide phosphorus 32 decays by emitting an electron whose maximum kinetic energy can be 1.71 mega electron volts. So maybe it is that. Maybe it's when they're calling it a beta emission as opposed to emitting an electron. Shouldn't that be the same thing though? The kinetic energy of the electron, right? You can release it with, in theory, no kinetic energy, right? It will be the minimum. Realistically, then it's not going to go anywhere, but right, it could decay. So honestly, I'm not sure why we're not counting the mass of the electron here, the beta particle. Although I will say, if we did count the mass of the beta particle, it would be greater than the original mass, so we can't. But I'm not sure why in this problem we're not, and the other one we are. Yes, there you go. Right? But it's the difference in mass becomes the energy, and the difference in the mass here is 0.12342. There you go. AMU. Right? And then we can convert that into electron volts. And our conversion is 931 mega electron volts. So 2 AMU, 1 AMU is 931.5 times 10 to the 6th electron volts. Which turns out to be 18,630 electron volts. Okay. Okay. All right. Well, good. I'm glad you figured out what you did wrong. So we know our error, so we won't repeat it. Nice. Okay. Number 23. We good here? I'm going to erase. Number 23. A uranium-238 nucleus emits an alpha particle with kinetic energy of 4.2 mega electron volts. What is the daughter nucleus and what is the approximate mass of that daughter atom? So uranium-238, uranium is what? 94? 92, thank you. Uranium emits a alpha particle, so that's a helium nucleus. Right, so that means this has to be 234 and this has to be 90, and I have it written down somewhere. TH, thorium, something like that, right? In this case, though, we are asked for the mass of that thorium atom or nucleus specifically, right? And we're given the extra energy, the kinetic energy of that helium atom. Right? The helium atom has a, where is it? Kinetic energy of 1.71, so we're going to go backwards. 1.71 mega electron volts. And we have to want to convert that into that mass, that loss of mass. This is the loss of mass. Right? This is the loss of mass. So that cancels. And 1.71 divided by 931.5 turns out to be 0 point. Yes. Isn't that what we're doing? Yes, you're right. I apologize. It's the same idea, just I used the wrong number. I apologize. What was it, 4.2? Okay, 4.2 mega electron volts. Uh, 931.5 mega electron volts. There we go. That's why I keep you around, Max. 0.004509. Right, so that's the extra energy. Right, so the mass of the uranium-238 minus the mass of the thorium-234 plus the mass of our alpha particle, equals that extra mass, right? Equals the energy. That's the idea here. So what do we got? 238.050783 minus the mass of the thorium plus the mass of the alpha particle, 4.002603 is equal to 0.004509. Yes. Is back there? Yes. Yeah, you're going to have to be, obviously, you're going to have to be given the appropriate mass of the given nucleus that you need. Okay. You can use what? I don't think so. Yeah, you'll be given anything in the problem. It'll be any information you need will be given to you. Right? You haven't memorized the periodic table? You haven't memorized it? No. No, it's crazy. I had an argument with the chemistry teachers for years about, like, when you took honors chem, just regular, did you do like element quizzes and all those things? I've argued for years. I argued with the chemistry teachers. This is the dumbest thing ever. You should not be doing this. This is a total waste of your students' time to do those things. That's right. How about instead of having you memorize a periodic table, you actually teach them how to use a periodic and read a periodic table. I argued for years. I argued with the chem teachers that is dumb and that you're wasting your time, that you shouldn't be doing this. Just teach them how to read the periodic table. I lost that argument for years. You're going to memorize, some of them you're going to memorize just from use. Right, you're going to memorize. But, you know, why do you need to know the atomic mass of, I don't know, some obscure, I don't know any of them. I know hydrogen, helium, oxygen, carbon. That's about the only ones I know. Okay. Right, we're good here though, and we're gonna just solve that for the mass. That's the idea. Right, I don't know. Okay. And in number 27, it's the same exact concept, except it's a beta particle. And like I said, when we did number 18, we didn't use the mass of the electron. In order to get the answer that the book is saying the answer is, at the back of the book for number 27, you want the answer here, Gio? I see you copying. I just didn't bother to solve at the end. I have it on my notes. But when we get to number 27, I'm not sure why we need to use the mass of the electron, whereas we didn't in number 18. And it pisses me off that I don't understand why. This answer turns out to be, by the way, turns out to be 234.043671 AMU. Okay. Okay. We good? Can I erase? All right. And number 27, like you said, is essentially the exact same thing. I'm not even going to erase the whole thing because I'm going to do that again. All right, it's just beta emission, beta decay. So we are given phosphorus 32, and we're asked what does it turn into during beta decay. So this has got to be 32, and this has got to be 16, and that turns out to be sulfur. Right, and we're given the fact that the beta particle, the electron, has kinetic energy of 0.71 mega electron volts. Right. So we do our conversion again. This time I get 0.001836 AMU. So that's my energy. That's wrong. 32, 15, 30, 32, 16. All right. And like I said, the thing that I don't have the answer to, which really annoys me that I don't have the answer. 973,907. The mass of the sulfur plus the mass of the electron is equal to why am I using it here, but I didn't use it in the last one, in the when we did the tritium, the beta decay of tritium. You would think I'd like it. It just seems, I don't know, contradiction to me. And I don't have a good answer other than the numbers don't work if you do it the other way for the tritium decay. And that's not a good enough answer. The only possibility is, right. Right. Yeah, that's what we're doing here, right? This is prior. and this is after, because this electron isn't an electron that was orbiting. It's not an orbiting electron, remember. It's a neutron that decayed into a proton, right? It decayed into a proton, so it went from 15 to 16. And it, in that process, it emitted a electron, which we call a beta particle. Right, right. But when we did number 18, the first one, this tritium, this one, right? And we were just solving for energy. But when we did it this way, right? The tritium decayed into a helium-3 by beta decay. And when we filled in here, we left this as 0. I'm sorry, what was that? I don't know. I don't know. My only thing is it specifically calls it beta emission in number 18, whereas in number 27, the one we're just doing here, it says it specifically calls it an electron, and I don't know if that makes a difference. Like, that's the only thing different I can see about the two. Which just annoys me that I don't have the answer to the physics of that. All right, this answer, by the way, just turns out to be my notes, 31.971522 is that. Okay. Okay. But again, the key concept here, though, is that loss in mass becomes the energy of the radiation. Good. All right. Half-lives, right? We did that little half-life activity, right? Anyone have any issues with the idea of a half-life? Right, the half-life is the amount of time it takes for half of the nuclei in a sample to decay. Right, it's the amount of time it takes the half of a sample of nuclei to decay. And hold on, I want to do this. Oops. Escape. Make that go away. Drag this over here. Right? So we get this, right? We get this curve that we all saw in our lab. Half-lives can vary from very, very, very short amounts of time, like to fractions of seconds, to thousands and thousands of years. Here, carbon-14 is, right, 537 years. Or I'm sorry, 5,730 years. So, and that's, all right. And then I had one more slide. I don't remember what the last slide was. Oh, decay series. In the process of of decay during that process of decay, whether it's alpha decay, beta decay. Things can decay into other things that are still unstable. So you get a whole series of decays until you get to a stable, nucleus, right? So here in this example, we started with uranium-238, has an alpha decay, and then that is still unstable. So now we have some beta decays and then a bunch of alpha decays until we finally get to lead-82 here at the bottom, which is then stable. Okay, that's just called a decay series. So the half-life of each, yes, the half-life of each the thing it decays into has its own half-life, right? So the half-life of the uranium-238, which is whatever it is going to go through its series, its own, period of time, and then each one from there has makes its own graph. So to get to that uranium or to that lead-82 at the end, it could take an enormous amount of time. Right. Okay. Your assignment for today is 4 questions and 4 problems on half-lives. Okay. There's 4 questions and 4 problems on half-lives. The problems are really just kind of fractions, right? That's not a specific thing, right? It's more fractions for you to do, right? Figuring out how many half-lives have gone by, what fraction is, right? Because a half-life essentially is 1, 2 to the x, right? So 1 half-life is a half, 2 half-lives is a quarter, 3 half-lives is an eighth of the initial stuff. Okay, I think you should be able to handle that. Get those 4 questions, those two questions, 2 problems, and then we'll move on to our last stuff in this unit. Right, my goal is to finish this unit this week and take the unit test Monday and Tuesday, and then spend the next 2.5 weeks after that prepping for the AP test on May 7th. Whoops, hit the wrong button. Where's my record button? Sorry, oh, there it is. Stop.